been bothering your brain that you think you know how to explain? You need a test. Yeah, think up a test.
In the discussion section, you will address your initial research question, consider the chemistry that is involved, and compare your results with those of other researchers. Begin by examining your AA results. Do the cations exhibit similar retention values? How about the soils? Are they retaining the cations to a similar or different extent? For this research group, the nickel retention is greater than the copper retention. Both the organic soil and the urban soil seem to exhibit similar retention values for these cations. For this research group, the lead and zinc retention are similar for the urban soil. However, they seem to be different for the ocean forest soil, with lead being more highly retained. In this example, the lead retention is much greater than the nickel retention. Both soils seem to exhibit similar retention values, however. Be careful with your analysis. Notice here the researchers incorrectly identified the cation that was more strongly retained. How would you characterize the retention in this example? These researchers correctly identified the copper being retained to a greater extent than the zinc. Both the Happy Frog and urban soils, however, seem to exhibit comparable retention. One way to connect your AA data to chemistry is to consider the characteristics of the soil. With the XRF data, you can consider the clay content in the soil. With the IC data, the cation exchange capacity. The soil organic matter values may also be important. With weathering, the primary minerals in soil are converted into secondary minerals. These may include clay. During the weathering process, the particle size is reduced. Sand particles, SiO2, are relatively large. Clay particles are much smaller. Secondary minerals may be more efficient at retaining cations. Clay particles are stacked in layers, like sheets of paper. The surface of these clay sheets is negatively charged. This means that cations can be retained on the surface of clay particles. One often finds that clay particles are effective at retaining different cations. The clay content in the soil is often related to the rubidium concentration. You probably have the rubidium concentration in your samples when analyzed by the XRF. Notice here, for the urban sample, the rubidium concentration suggests a clay concentration of about 14%. The other sample is much lower, with a clay content closer to 3%. You will probably find that your urban sample has much more clay in it than the other sample. If your clay-rich sample exhibits greater retention, you should discuss this. What if you have different results? It is reasonable to state that the clay concentration does not appear to be an important factor affecting cation retention for your soil samples. A soil sample will be retaining cations. The more negative charges, the greater the retention. In this example, the soil depicted on the right would have a smaller cation exchange capacity because it has fewer negative charges that can retain cations. Your IC data provides information on the cation exchange capacity for your soils. Here, the cation exchange capacity is much greater for the other sample because it had far more cations that were extracted in the IC analysis. It is possible that the greater cation exchange capacity is a contributing factor leading to greater retention by the organic potting soils for this research group. If your results are different, you can once again discuss them. Perhaps both of your samples exhibit similar cation exchange capacities, or it appears uncorrelated with your retention values. Either scenario would be worth discussing. Organic constituents in your soil may also lead to greater retention. Humus, which is partially decomposed organic matter, may be affecting the retention of cations and water. Don't confuse this with hummus, a tasty treat made from chickpeas. You have measured the soil organic matter concentration for your samples. Are your values typical? To find out, you may want to compare them to those of your classmates. Remember that these data are listed in the class-wide data set. Returning to the class-wide data set is a good way to compare your results with those of other researchers. Another good way is to compare your results with the provided research article. The Fonts Research Group has conducted an investigation very similar to ours. Looking at this paper is a good way to learn what a scientific paper looks like, and also to find data that would provide useful comparisons. An easy comparison would be to consider how your cations are being retained relative to the values that Fonts reports. You will probably find that these Brazilian soils differ from those you have analyzed. They probably have a lower organic content concentration and also a much higher clay content. The data in Table 4 is very similar to what you have collected. For different cations added in different concentrations, you can see the amount that was retained by the soil. The values are reported in ppm. These indicated values show the amount of lead or zinc that was retained when 5 ppm was added to the different soil samples. Here's an example of data collected in our investigation. The lead and zinc retention is similar for the urban soil, but lead is found to be retained more highly for the ocean forest soil. Is this typical? In comparison with the Brazilian soils, one finds that lead is strongly retained. What is unusual is that zinc is also strongly retained for the low contamination level samples. Comparisons like these will help your discussion section. Finally, there are many different ways to examine your data. Share your ideas with each other. Your careful work has produced an extremely authentic data set. You will probably find that there is not a single right answer in your analysis. Your data may support some ideas or theories, but not others. It is fine to discuss both cases.